Hello? 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 Oh, here we go. Right. Morning, afternoon, lunch. So we've managed to get through now two of the assignments. What I'm going to do today now is run through a little bit of the, give you an overview of the marks, and just go back to C1 and then go over C2 and just remind you of what the structure of the module was. Give you some feedback on C2, just general, so how you did, where marks were lost. Two sets of groups have been released this morning, so you should have visibility if you're in the first 1 to 16 groups. The other two will be released this afternoon. What I'm going to run through here, to have a reflection on C2, and then get you starting to think about what you're going to do for your last assignment on the module C3. So just to remind you of the 3 learning objectives. Advanced technical reporting, which is very much at the heart of all of this all the way through, but what we were trying to do was make sure that you were lined up a little bit to the way that we would like to see the technical reports coming out. So from your first assignment particularly, there was a lot of emphasis on the actual report writing itself. Getting more experimental practice, different types of experiments, so that's learning objective 2. And now we're going to be heading on to learning objective 3, which is to look at how we're going to use the computational modelling that you've done, that you've learned how to do in ANSYS, and how we do that, and how we're going to compare very explicitly with the experiments that you've done. So overall, you should know this by now, you've had 4 experiments so far. There's a few of you who's just going to finish off the last experiment. E1 was the aerofoil experiment. That was aligned to C1. That was worth 20% of the module credit. You've got experiments E2 and E3, which went into your C2 assignment. That was worth 30%. That was aligned with the experimental practice learning objective. We had a 4th experiment, which was more hands-on, which was the bolted joint experiment, which had a pass-fail online test. And as I said, there's two sets waiting to do that at the end of this week. And what we're going to do is give you some feedback next Monday on the bolted joint experiment and on the marks and how you did on the bolted joint. There have been a couple of questions about what the pass-fail criteria should be. We're going to keep it at 75% until next week, and then we're going to look at all your results and see how you do and see if we lower that. Okay? In parallel with the experimentation, you've all done the beginners to advanced ANSYS tutorials, and now these are going to be combined. We're going to combine the experimentation, particularly E1, E2 and E3, and you're going to choose one of those experiments to undertake the C3 assignment, where you're going to compare the model results with the experimental results, and hopefully with also some more insight into the empirical physics. So this is just a recap of just before the Easter recess. We talked about the C1 assignment. That was the breakdown in terms of the sort of marks. Pretty typical, 18% in the third, 36% 2, 1, 42%, and then a small fraction getting first and distinctions. We went through a number of different parts in which, sort of as a whole, as a group, all of you were failing in certain parts of the submission. That went on a variety of different parts. So summarising what was in the report was something that you were struggling with a bit. The referencing and the research that goes with the referencing was also something that you tended to struggle with it a bit. And often figures would come through that weren't very clear, didn't have units on them, and so on. So we went into a kind of breakdown of the entirety of the comments that went back to you in terms of the feedback. And I must say that there's been an improvement from C1 through to C2, but as a whole we're sort of still failing in certain parts, which I'm going to go to now. I'm not going to run through all of those now because we did that in a previous session. We always get a distribution of people. Some people want to go off and do their own kind of report, and they don't want the sort of very structured layout that we've offered to you. And that's fine. And no one has been penalised for giving their own format of the report, as long as it contains the basics. And in fact, I would encourage it, certainly for this last report, to think a little bit out of the box, and you're more than welcome to change the suggested format, as long as you don't go over the 10 pages. If you decide you only want to put half a page on the experimental method, because you've already talked about it, yeah, it says 2 pages max, but if you want to keep that at half a page, absolutely fine. But it does need to have some bare bone details in there. You know, you are comparing an aerofoil experiment, so it's very important that you know what the shape of that aerofoil is, and also where the pressure taps were. And then you always have to think about who's going to be reading your report, why are they reading your report. So imagine there's somebody out there who wants to replicate your results, and all they have is your report. In order to be able to replicate them, they're going to need to know details. If they don't know what the foil looked like, they're not going to be able to replicate those results. So if you put yourselves into the foot of the reader of your report, it'll give you an understanding of what it is that you have to actually explain. Right. C2. So the reason that Dr. Quinney and Dr. Jeffs and Dr. Roy are here is because if you've got any specific questions about what I'm going to present here, please ask them now, okay? You can, of course, come and see us in office hours, which are still fully there until the end of term. So the breakdown on this was, it followed quite a logical distribution. Got about 16% had firsts, and then two ones, about 33%, 28% in 2 twos, and then a rather larger than I hoped distribution on some of the people getting less than 40% of the marks. So this shows that, and I'll give you some of the typical mistakes, but overall I think there is an improvement from C1. I think that a lot of the feedback has been taken on board, but it does show that all of you really need to do well in your C3 assignment, because that's the big one. It's worth 50% of the marks. So cruising through at this stage is not an option. Getting this last one right is something which, hopefully with all the feedback that we're trying to give you as we go through, you'll be able to build up those marks to where you want to be. And certainly what we don't want to have is any fails at the end of the module. Common mistakes, and I've picked out from comments from all of us here. There may be some more, but so I'm just going to go through it sort of in a structured way. So typically the summary, a lot of you are confusing the summary for an introduction. So it tends to be long, waffly, starts off with, air engines are very important for aerospace because they keep planes flying, and a summary is a summary of what is in the report. So you want to have an aim, you want to have a brief description of the experiment and the method, how you collected the data, and then you want some concise summary of the outcomes. How they compared to empirical data. So something as well is in the language that we're using as well. There's a lot of colloquialism, contractions, not very good grammar, okay? And I know we're engineers, but I think we can do better. one of the things to focus on is that when you write the report, it's expected that you're normally writing the report after you've collected the data, so you should always be reporting in the past tense. And I think that a lot of people have gone ahead and kind of written the summary before they even get the results and do the report, and they don't go back to the summary and change it to the right tense, so it's in the wrong tense. Sometimes you might say the outcomes of the experiment are as expected, but that's not really a good enough statement, because you have to say what is expected, what was the expectation. So you have to be a little more detailed. Still a bit of mix-up, and I think it's probably a little bit of how the template went out. We had summaries and objectives, and I hope we kind of cleared that up in C1. So the objectives are a breakdown of the study, so you can have a lot more detail on the objectives than you would do in the summary. Okay, and it's good to have them bullet pointed at the end of it, and a lot of you have done that. Often, if you want to keep your summary concise, you'll have two statements. So the aim of this experiment is to look at boundary layer flow and measure the boundary layer thickness and compare it to theory. That's fine. That's the aim of the experiment. But then you have subsequent broken down objectives within that you're going to analyse how good the experiment was in terms of the repeatability of the experiment or any errors that you might expect. So I still strongly suggest that you have that format in your next assignment, whereby you have a concise summary and then you bullet point your objectives underneath. Remove guidelines and rubric. I know you're all kind of under pressure, there's a lot of work and stuff, but you do have to do that. Sometimes you see full tranches of text still left in there from the template, which has obviously been done in a lot of a hurry, but it makes the report look awful. And it's a giveaway. You just got to do. The experimental section is one where a lot of you are putting a lot of detail into the experiment and the description of the experiment. Possibly detail which is not that significant in terms of replicating the results. So the significant details really are where were the foils on the boundary layer experiment. So if they were located at 40 millimeters, 90 millimeters, 150, 220, 300, that either has to be stated explicitly in the text or shown preferably as a sort of diagram. Some of you have taken that from the user manual. That's absolutely fine, with appropriate reference, that's fine. But that detail does need to be there. And that detail also is the same for the stress concentration experiment. So often you've said, here's a picture of my test bars, and you haven't put, what is the size of the hole, what is the size of the gauge length, the thickness, a lot of the details that would mean that somebody who was going to try to model that or replicate your experiment wouldn't be able to do it because they wouldn't know what the length of that test bar was. So, those are very much the essential details of what you need in the experiment. Health and safety is not. So I've said that for C1, and we've all said that for C1 and C2. A lot of that was put on Blackboard. It is important that you know that before you go in the lab so you don't hurt yourselves, but it's not important as far as the outcomes of the experiment. It didn't modify the outcome of the experiment. So you can get rid of that and just think, C3, you don't need to talk about health and safety, okay? All right? It's good that you know about it, but you don't need to include that. And sometimes that's been as much as a sort of paragraph, which has taken away space from your report. Okay. Sometimes big chunks. So yeah.
I think the reason people have included health and safety is because it's in the template, but it's not so relevant. It just definitely gives you attention or something, but it's in the template of the experiment.
Is it? Okay. This is a. Okay, well, take it from me. It doesn't have to be. Okay, I did try to say it last time. We've got a lot of data, a lot of kind of information for you there, trying to give you as much information as possible. Sometimes we forget to update in different locations, but honestly, you will not be clubbed for not mentioning health and safety. So now I said it, it'll be recorded, it'll be on Blackboard. Let's take that as a definitive. Okay. I'm more worried about some of the basics which are missing, and obviously that is where The few of you who have failed, often it's been a major part of it is because you've missed out going for kind of any attempt whatsoever to talk about stress concentration factors, for example, and that is something which, even at a very basic level, you could have tried something at it, or not comparing to the theoretical boundary layer thickness from one of the two. So that's sort of a big loss of marks. It's more difficult to talk about the reliability and repeatability without going into many more samples and experiments which have a longer duration and all this sort of thing. But you do need to pay some attention to that. So, for example, with stress concentrations, you only have 2 repeats of each sample, which is obviously not ideal. But one of the things you can point out straight away is if you're trying to work out what standard deviation is, how many samples do you need? What is the minimum number of samples you would need to get a standard deviation? Okay, I'll leave you work that one out. Yeah, but have a think about what, in terms of the statistical, how many is the minimum sample points you need for a standard deviation? You know, and that would be an immediate problem with the experiment. Is you can't work out standard deviation because you don't have enough samples. But what is the value? What is the number that you would need? There's still some confusion, I think, with boundary layer. Zach, you mentioned in terms of the transitions. So I think a lot of you, from what I saw when I was marking, so you talk about the transition between laminar and turbulent, and some of you picked it out. So you worked out your values from the laminar equation, and you managed to pick out your values from the turbulent equation, but you haven't just sort of really explained carefully why you've chosen that as a transition. So that's kind of like getting down into the nitty-gritty of why. And I think it's still quite unclear to me, but at least I would probably say it's highly likely there will be a transition between these two values. You're measuring atmospheric values, those are often not included in the data you're putting in. Right, graphs, just to give you an overview of what I would consider to be not so good and a bit better. So when you're doing low displacement curves, there's a lot of points, so you'll have thousands of points possibly. Don't put big markers on them because you'll just cover up all the curves. So that one on the left up there, a lot of markers on there. You can't even see the curves below it. Immediately it starts to look cluttered and you can't really make head or tails of what the data's doing. So it's better there that you just say, right, no markers on that, straight lines. Another problem is that the lines themselves that you choose might be too thick. You know, if you use some of the default settings for Windows 10 or Microsoft, whatever it is, they come with really thick lines sometimes and they all cover each other up and it's very difficult to see what's happening. And you've got to go back and say, right, I'm not using that default one, I'm going to use a more scientific plot. I think on the right there, you can see a slightly better, and I know there's a lot of graphs superimposed upon there, but through the differentiation that the author of this one has done in the colours, you can sort of automatically pick out which of the stress concentration or which of the holes in the samples are on which. And also, sometimes with the displacement, you might get the odd little small negative value, but that means that on the axis there you've got minus 1,000 Newton or minus 1 kilonewton. That doesn't need to be in there. That's just a bit of experimental error. But what it means is you've just added yourself a lot more data onto the graph, makes it more difficult to read. So those are just kind of very, I've seen that again and again, which is why I'm bringing it up, because, you know, another horrible default on Excel is, and apologies if you recognize your graph, okay, don't put your hand up, but I needed to show you quickly what I would consider to be not so good to better. One of the horrible things that Excel does is it'll often try to put smooth curves onto data. And when you've got a lot of noise in your data, and you sometimes don't know whether that's physical error or not, it might be correct, is if you put a smooth curve, you start to read into that, you think, oh, that's a nice smooth curve, and you start to read into the physics of it, and you go, I don't make head or tails of that, it's because the smoothness of the curve itself starts to confuse you. It's actually fitting a curve unrealistically onto your data. That can lead to problems, because you'll start to interpret it as being possibly correct. You're going to start to think, oh, that looks like a nice smooth transition from laminar to turbulent, that must be right. And it's actually, well, no. There's a lot of things on the line that could be wrong. The datum could be wrong. So your transition point could be, you've got, plus or minus 20% on either side of the point, and it just happens to pass through it. So, a bit better, the second one on the top, and then what I would call slightly even better there, because it's a little bit clearer. Again, it's this default theme colouring that Excel tries to get you into with using smooth curves and sort of trending colours. I think you need to have a good differentiation and also a systematic way of either putting lines with dashes or straight lines and making sure they're not too thick. This one on the left here, you can see really thick lines there, and it's quite difficult to sort of differentiate between them. The final thing is, the best one here, it's also got some form of error bar on there. And that immediately starts to tell you, well, that's actually from the experiment, so you can quite quickly look at it and say, that's my experimental variation. So anyway, that's any other comments on graphs? No? Okay. Right, references. Now, the reason references are important is because they show how much you've looked into what you're doing, the theory behind it. Sometimes there's not very much there still, and you're losing most of your marks, even on the top ones are still not being referenced properly. These long, I think it's, I don't even use the same citation software that you've got, but there is one that puts in the link, and it looks terrible, absolutely terrible. And in fact, sometimes you can't even follow the link anyway, because it's split the link up over various lines. So it's actually pointless having there, and it's actually not part of the Vancouver or the IEE to have long links like that. So I think sort of the main problem is that often you're only picking out one reference, two, and the rest are coming from books. That's okay. There's a lot. It is better than it was, I must say, but it still needs this basic. You need to know the author, the title, journal, year, page. Not necessarily that huge big link at the bottom. So your references should look as good as the rest of the report. Sometimes it's mainly in the discussion section for either of these where you should be bringing up the references, and that's where you should have 2 or 3 key references which are about the same experiment with a similar Reynolds number, and it's honestly not that hard to find, and most of you have found 1 or 2, but not necessarily then, even if you have, you may put down a list of references at the bottom, but then you haven't linked it into the discussion. So you may have read it or said you've read it, but you haven't necessarily made any link in the discussion. You haven't made any comparison to the data, definitely no validation of the data together. So that's still, when I talk about references, I'm not talking just about that little bit of text at the back. I'm talking about the actual comparison of the data that you're making. So, I think that covers it in terms of the general sort of, have I missed anything? No? Okay. So what we have done is have a look through your personal reflections, and we're using this as an indicator of how you're finding the work, the experiment, the assignment, the experiments. Also, you're helping us improve this for future years. So, just to always say thank you. It's a good thing. Doing a personal reflection, some of you have used that to be able to look at your own work and the own experiment and how you've done it and how you think you've done it. So there's that kind of self-evaluation, which is a great part of it. And then there's also the reflection in terms of what we can get as feedback. and how we can improve things as well. So I've divided this down into generally comments which are either from people who are obviously happy with what's happening in the module, to people who are not necessarily that happy with what's happening in the module, and to the reflection whether it's a constructive or a destructive criticism. And I'm pleased to say that there's not that much destructive criticism, and there's actually a lot of very happy people, and I'll show you some of the numbers in a minute. But also some really, really good suggestions for how to improve it. And you wouldn't believe this is more valuable than any NSS survey or anything else you can find, because this specifically targets this module and how we can improve it next year. So, I'll pick out anyone in particular. Saying that this time on this semester could be better utilised was, I found, a little bit depressing. On the other hand, I found even people who weren't particularly happy with the module still had some very good criticism about what to do about experiments. I'm not going to run through all of these, but we did ask, sort of on the reflection, to consider 3 points here. What have you learned about experimental testing? That's your own personal reflection. How does that hit the original learning objectives? Okay, that's a kind of mixed. And then the third one is how can we improve it? And that's our feedback to us to be able to improve it from now onwards. 93% of you were very positive about the work, and some of the comments on here that reflect that. Just picked out a number 4 from there. Module was enjoyable and had parallels to what was being done in industry. I like that. That he actually is gearing towards that preparation. He's not there just to bust you. He's not there to tax you. He's to try to help you through the technical reporting. And again, that emphasis on how it gets done in industry, which is, I think, actually quite true. In terms of how to achieve the learning objectives, fully and mostly achieved. For learning, so LO1 and LO2, on the whole, most of you thought that it had been achieved, so that's quite a high percentage of you thought it had been achieved. A few, partly, and I think some of these I picked out, for example, hands-on, that the experiments weren't hands-on enough, okay? There were a few of these comments, and it's not the first time in the years that we've had this module. It's become less and less hands-on, I'm afraid to say. This set of experiments, E1, E2 and E3, were all done on the wind tunnel and on the stress concentrations. We don't have time to let you go and make your own samples. We don't have time for you to go and make your own aerofoil and put it into the wind tunnel. It takes a lot of preparation. It was done before E4, which is more hands-on, where you actually make your own samples. But after we've got the module out of the way at the end of term and come through June, August time, we're going to have a sit down and think about the main feedback from you, and one of those being it for more hands-on. There were some really good suggestions. So to let maybe one of these experiments, like something like the bolted joint experiment, be planned by each of the groups throughout a lead period of term, so you can actually plan your own experiment and go in and do your own experiment. Not necessarily bolted joints, but maybe the stress concentration experiment, you design your own stress concentration features or samples. I've always wanted to be able to have something where you put thermocouples in there and you actually go and do something which is more hands-on, but it is really difficult to do with almost 200 students on such a short period of time. But yeah, so basically here are some of the breakdown into more samples to be tested, requires more time. More diverse experiments, that is quite a difficult one. Better experiment equipment, more in-depth guide possibly to getting the experiments on. I think the more hands-on is definitely something which stands out, which I'm going to try to see if we can do something about next year. But there were quite a few of you who put down there could not be much more improvement, which was really quite nice. So thank you. That's it in terms of C2 so far. The rest of the grades will be out this afternoon or tomorrow. Any questions on that so far? Is it good me going through that kind of feedback generally, yeah? Yeah? Okay. Because we'll do the same then with quality joints next week. What I'm going to do now is just run you through some of the preparation for C3 and a little bit on computational fluid dynamics. And then I'll let the guys disappear if they want to. It's boring as hell sitting here hearing me talk. Then we'll go through a little bit of the stress concentration theory that might be good for the computational validation of the stress concentration experiment next week as well. So this is the plan for what's left of today. So I'm not sure. We've only got 20 minutes, so I'll try to cover this quite quickly. What I don't do now, we'll cover again next week. So you've still got a number of weeks until the deadline for C3 anyway. Yeah? Okay. Right. C3. So this is now putting everything together. Okay, the models that you've worked on with us in the labs, and the experimental data that you've got, your own experimental data that you took with your group. It's going to be a 10-page report, and you will pick one of E1, E2, or E3. And you will compare it with your computational results. So this 10-page limit we suggested the breakdown on the right-hand side there, but you do not have to stick to it, apart from the cover page, obviously. Okay, and don't include the cover page in the report if you don't want to. I don't care. You know, it's just 10 pages for the content of the report. Okay. It's up to you. I would suggest you kind of stick to the summary objective breakdown. I think that's logical. But experimental description, you've done that already once at least, if not twice. So you can cut that down, but just get the absolute fundamentals of what you need for the modelling and for someone coming afterwards. Computational methodology is a new one in terms of what you've reported so far. So do spend a bit more time on that, and I've got a bit of a breakdown later on that. Obviously results. Now if you need more than 2 pages, take away from there somewhere else. Cut the half page down on the experimental methodology down to half a page, and then have a page and a half more on results, or a page more on discussion. That's up to you. Okay? Okay, the deadline is 5 p.m. on the 11th for all of us. And that's it really. So I think just looking down at the breakdown, you've got 15 marks going on the structure and 35 marks going for the technical content. So now it's becoming more skewed towards the technical performance in the results rather than the formatting. But still, I would hope to see that with the feedback that we've given you from C1 and C2, that you have addressed most of the formatting that is required for C3. I've got a number of examples here. This is just going off a bit about talking about computer-aided engineering and why we use it. And it's just to kind of summarise what we use it for. Because often you have to manage expectations of people who might consider themselves more experimentalists than people who might consider themselves more modelers. Experimentalists would often point at the modelers and say, right, you give me all the answers and then I'll go do the experimentation. And then the modelers would turn around and say, no, we can't do everything, you guys got to tell us, you know. And the fact is that it's a tool. It's only as accurate as the validation that goes with it. And not understanding the physics of a problem is not an excuse to start modelling it, if that makes any sense. If you don't understand the physics of a problem before you go and try to model it, you're not going to get anywhere trying to model it. And that is one of the biggest problems that you have with industry, is if they don't understand something that's going wrong with their process, they'll come and say, right, you model it and you're going to tell me what's wrong with my process. And sometimes it's not even something that you can capture with models. or even the models that you would need to capture what's going wrong would be so complicated that you would need some impossibly big computer time, and they want to capture everything from thermal to phase change to liquid to stress to everything together. So any modelling that's done, in my opinion, and that's why in this course we are harping on about the validation, needs to have validation. And without that validation, often models are not that useful. This is an example of, well, actually most of these examples, or 4 of them, are from when I worked in one of the projects which is running here. It's called Astute, you may have heard of it. And they run a lot of modelling exercises with local companies, and this is one of the examples. This is a lead recycling facility in Ebervale, and they were looking at, well, improving the behaviour of their cyclone, which would take small particles of lead which was coming off furnaces, and it would making sure none of them can go out into the environment, but they wanted to make sure that they could do this filtration in as an efficient way as possible. And this is a classic example of what you would use in Fluent. They could help to optimize their furnace temperatures and the particle sizes that are coming out and how many particles were being trapped in the cyclone. So the CFD itself was very complicated, so you had phase change in there, particulates being transferred, coming through, then you had multiple mixes going into quite a complex cyclone. But I remember when they first came to us, they said, "Oh, you can quickly put this through your model." Just getting the cyclone CAD'd up took the best part of half a year, and a lot of heartache from the guys who were doing it. Something closer to home. This is Canal Cardio. It's a spin-off from Swansea University, and they're designing a ventricular assist device, which is there to help patients with severe heart failure by pumping blood around the body. So on the other extreme of things, down on a very small scale, but still very complicated, non-Newtonian blood flow, so the fluid doesn't behave in a Newtonian manner, and they've designed many design iterations and manufacturing iterations to get the design of the blades absolutely right, so that they don't cause hemolysis in the blood, which is a breakdown of the red blood cells, or growth of plasma. So again, it was used in a non-validated manner, to a certain extent, to improve the design in multiple iterations. Another one, which is thermal fluidic. So this is looking at the position. So these engines on these, this is a company which has sadly gone out of business now. I don't think it was our fault, but when we did the work for them, it was an interesting use of CFD, and the guys who were running the company were very interested in the kind of results. It was being able to locate the twin engines that they had inside the engine rooms in such a way that you kept the intake for the engine at a sufficiently cold temperature. So what they were finding is that their ships were incredibly efficient when they went up north towards Greenland, but when they went south down into the tropics, they lost all their efficiency. And so they were looking to try to optimize the location of the intake air. So I was actually quite proud of this, because with this one here, I was actually in that engine room out to sea, locating thermocouples on all the engines, because of course I said, you can't have a model unless you validate it. So he said, yeah, off you go. So quite a rough sea, stuck in the engine room with quite a high temperature, lots of fumes, and sticking thermocouples and infrared cameras all over it. But we were able to come up with some configurations which allowed them to choose how they would align the engines and the intakes and stuff in such a way that the temperature would be optimal for a given atmospheric condition. So the guys who ran these models were running turbulence models, like you guys have done in your 2 tutorials, and they went through a whole host of different models until they validated properly. And when they validated their models, then they were able to change the configuration of the room with the models, obviously in a way which couldn't be done if you were building, you'd have to build hundreds of engine rooms to be able to find that optimal location. So that was used. One last example is the use of stress analysis to look at failures in dies, and this is for injection moulding tool. And this is one which we did with another local company called FSG Tooling. So these models would take weeks to run on the cluster. There's millions of elements. I'm glad to say that we actually did make a difference on this one without the company going bust, and we were able to help them redesign the cycling here and some of the sort of fillets were being used around where you would get stress concentrations. Stress concentrations, stress analysis, CFD, turbulence, it's all there, right? So you're doing it, and you're getting more of that done in this module than you have done before, and any other students before you have been able to do from Swansea. So you guys know more about ANSYS at this stage than all your predecessors. Yeah? So, how we do for time? 10 minutes. So we use the modelling to understand the underlying physics. Yes, we don't go into it blind. We know more or less what the answers are going to be. So validation is very important, and you can't really optimize to get better performance without. So if you're doing it for efficiency or improving a system, you need to have a validation point through which all the rest then you can use the model. It can be used for improving the efficiency of existing components. You can bring in multiple different physics, but you have to bring them in a controlled fashion and validate the heat transfer. You've got to validate the fluid flow with anemometers, with pressure sensors, whatever. Improvement of components to reduce failures, improve designs through incremental changes for efficiency. Right. I'm really not going to have time to go through all of this now. So you are going to be able to get the slides. I think you know what computational fluid dynamics stands for. We've been through it enough. I may have shown you this before as well. So we have the breakdown of the fluid equations, the inviscid, viscous. You've seen those in the tutorials, the fluid tutorials. We'll have typically either a laminar, which is the default ANSYS setting for fluid, and then you'll have your turbulence models, and then you can apply that internally or externally and throughout the different boundary conditions you set. Everything hinges on the Navier Stokes equations, which are in three dimensions. And we'll have the continuity equation, and we'll have the momentum equations. We're going to run through that. Reynolds number, turbulence. I have run through this before, or am I doing that in my head? Have I run through this with you? Have I gone through this step by step? Sometimes I think I have, and then sometimes I forget. It's all becoming a bit of blur over Easter. Determining the Reynolds, I think I have, because we went through it in the ANSYS tutorials when I was going through why we're using turbulence models. So you have seen a little bit about it before. So the breakdown onto turbulence is determined by the Reynolds number, as you know. Now, when we model it, we're looking at time averaging, and we used a breakdown of the Reynolds Navier-Stokes equations into the Reynolds average Navier-Stokes equations, and if you were to look at the backward-facing step, which was one of the tutorials that you were given, if you would have a camera which would tell you instantaneously where all the turbulence was, you'd have something looking like that, which would be very difficult to model. Okay? You can get very sophisticated turbulence models which will try to do that and capture every single fluctuation of the turbulence within it. But our models, our engineering models, are typically like the K epsilon model, which I've predominantly used, will give you some sort of time averaged value, like the one below. These are the Reynolds average Navier quotes, so I thought we'd derive them now quickly, and then move on. Not. They're very similar to the Navier-Stokes equation, so you still have a continuity equation and you have momentum equations. But in addition to that, you have two turbulence equations, and those turbulence for the K epsilon model will represent fluctuations which you try to capture. I'm not going to go through all that, just to say that you can simplify them so that when you solve ANSYS Fluent, you are actually solving the Reynolds average Navier-Stokes equations, and everything is very similar to Navier-Stokes, except that on the right-hand side you have a value called, which is modifying the viscosity, it's called the turbulence viscosity. Right. As you know, there's a whole bunch of different models in ANSYS, from zero equation, one equation, all the way to much more sophisticated equations. We have seen some of those in the drop-down list. We've concentrated on the K epsilon model, which is the next one. So if you're interested in the equations, they'll all be here later on the slides. I don't expect you to put these into your validation report, not with 10 pages. That would probably take up 10 pages to spin the equations in. But just to have some recollection of what it is that it means to use a turbulence model. Where are those equations coming from? Now, the process that you go through is similar to most modeling throughout different packages, but you have to describe the geometry, which might come from CAD, the flow conditions and material properties or flow properties. You have to select your models. You have to put in initial or boundary conditions. Then you generate your grid. You may have generated it beforehand, like you do in ANSYS in the design modeler. Then you will select some of the numerical parameters which you need to solve the problem. Then you'll do the flow solution, and then you'll do your post-processing. Okay? So, why do we need to know that? Well, you need to know a little bit of the background. You have seen the Navier-Stokes equation before. Is this the first model you've seen the Reynolds average Navier-Stokes? Yeah? Okay, that's what I thought. So that's why you're only getting a flash introduction to it. The reason that you've been given turbulence models now, which is kind of running before you know how to run, running before you know how to walk, is that, as you know, in our wind tunnels, mostly what you're getting is turbulence. You're getting turbulence coming in, and you're getting the turbulent effect. You would not be able to get very close to the answers if you weren't using turbulence. So those are in the ANSYS tutorials 4, 5, and 7 and 8. Right, so I think I've got about 4 or 5 minutes just to run through this and get a couple of hints. So with the computational methodology, now it's coming down to the actual C3 report itself, okay? So I would prefer to see your own sketches of the geometry with boundary conditions. I don't mind if you use something coming from sort of a TIFF or JPEG image that's coming from designer, and then labeling up on that, that's fine. You definitely need to address kind of some of what's going on in terms of the simulation. What turbulence model was used, so you can go back to your model and fish that out through Fluent itself. There are certain specific values that you put in. So you may have changed the air density to match your atmospheric conditions. You may have changed your velocity, boundary conditions to match your velocity in the experiment. So you've got to state those. A little bit of how you run your model. So listing some of those steps is a good thing. Accuracy. Did you do a mesh sensitivity check? How are those sensitive to boundary conditions? So this is now starting to get on multiple runs. A little bit about ANSYS and how it solves equations. So at any stage, if you go on ANSYS, you can pull up help and you can get yourself sort of a top-down reading of the manual. will give you more of an insight. So is it finite element, finite volume, finite difference? Was it 2D? Were you solving a transient flow, steady state? With the results, so a little bit of this is, obviously you need to put in the different velocities that you used in the experiment. You need to match your flow conditions in the experiment as close as possible. So by using the same density for that atmospheric condition, that gives you a good link into the right air properties. The validation, how are you going to do that? Obviously you're going to check, I'm going to show you some graphs now, you're going to check against your own experimental results, but you also need to still be including other people's data, which might be better than yours. So if you were looking to match drag and lift, you could do it like that. And that's one of the things I've noted as well, that a lot of you see, if you would actually call that a very, you guys are calling that a poor experimental comparison, when in actual fact it's actually not that bad. Okay, so anything within 20%, as long as it captures the trends and is close within 20%, is not necessarily too bad, but you know, room for improvement, but not terrible. So here there is results from two different models, a 2D and a 3D. So you guys can stick to 2D. You have got a 3D model on the server. It's there. It's up to you if you want to use it. But capturing the key features here, which is the fact that you've got increasing drag, which continues to increase past the stall point. You've got a stall point. Yeah, you've got to determine where the stall point is for yours, where the stall point is for the experiment, where the stall point is for your model. What is the peak lift just prior to stall? Now, if you're really brave, and I'd love to see this, if you can take one of your pressure profiles and compare it to the model pressure profiles. Okay? That would be a big plus. You'll have to get the pressure right. Now, you know there's various ways that you can output pressure from fluid. There's also various ways in which you can report pressure from the experiment. Yeah? But you can see that more or less the trends are there. But how can you get that to actually superimpose? With the boundary layer, I'm literally down, oops, I'm a bit late now. So with the boundary layer, you will see some things that you think, well, that's an anomaly, but actually, no, it's not. So one of the things to remember is that often the theory, like Blasius, is not representative of the experiment you're doing. But the modelling you're doing is representative of the experiment. So you may get better results from the model than you do from anything that you're trying to do in terms of theory. So that overshoot that you get, for example, there, is a perfectly physically real phenomena, but Blasius doesn't capture it. Okay, I'm not going to run through that. When comparing, I've put there modelled versus experiment, and the experiment I fitted with a straight line. I haven't tried to join the dots with some wiggly curve. I've just put a straight line through the middle of it, just to see if that got me any closer to the trends. Discuss trends. Don't try to copy this because I put no. Sometimes I'll not put units on there on purpose. All right, that's for you guys to get right. How could the modelling be improved? Beware that mesh sensitivity, so refining your mesh doesn't always give you better results. Refining your mesh well might do, but fluid dynamics is a very non-linear problem, and you might not be able to get better just by refining your results. So the three main things looking for in the conclusion: how does the data compare to any published experimental data? How does it obviously compare to your own experimental data? How does it compare to theory empirical, and how reliable are your results? So those, actually that's really four, but those points need to be addressed. And it's not good saying, as expected, you've got to have some sort of conciseness. So our drag forces were within 20% or 10% or something like that. Okay? Can I run through these things? It is okay for the experiment, I said cut it down briefly. It's okay to repeat what you had in C1 and C2, but just keep it really short. What else is important here? References, 2 or 3 good references. Okay, make sure there's similar Reynolds number and it's the same experiment. Don't choose a different experiment. Okay, that'll do. We'll do the rest next week.